Mark P. Otten back with you. Okay, welcome to the extended version of my data screening video. I do have a shorter version that I use for my undergraduate stats class. This one is more for my graduate students who are working with larger data sets. This is my data screening guy. He's trying to screen his data. Anyway, it's a different kind of screening, but you get the idea. So we'll get into it. So you guys may have seen a lesson on this before, or you may have, hopefully actually, have enacted bits and pieces of this in your data analysis that you have done before today. And that is making sure your data is clean and ready to go before analyzing it. This is something that I kind of learned the hard way. In my first couple of years in grad school, I really wanted to just cut to the chase. And so I just put a ton of data into a huge correlation matrix for fun and to see what came out. And then one of the senior grad students in my research group at the time was like, "Mark, what are you doing? You need to check this first." And he was like, kind of like forceful. And I was like, "Who is this guy?" But then I realized that he was right. And it's a process that needs to be taken seriously. It's a process that, well, you just need to kind of look at your data before you jump in and start analyzing it. And so there's some things to look for. Missing data we'll talk about here in a second. Univariate outliers. A univariate outlier is something that an outlier that exists in one column of your data set only. That's the thing that's most often screened for. But then multivariate outliers are also important to screen for, especially in larger data sets. And then the equality or homogeneity of variance assumptions need to be tested or evaluated when you're comparing multiple groups, as in a t-test or an ANOVA. So that's what's on the agenda for this video. The first one, and often you can kind of jump around here, but the first one is usually just looking at your data set, like I said, looking for missing data, first of all. So if 5% of your data or less is missing, then you're okay. Tabachnik and Fidel, the wise women on our, that wrote the textbook, Tabachnik and Fidel, say if 5% or less of your data is missing, you pretty much are going to get the same result regardless of what you do. But you still need to look for that missing data and make a decision either way. It's just that when you have a small amount, the decision that you make is probably not going to have a huge effect on the results. So what if more than 5% of your data is missing, or it's not missing randomly? Now you can check for randomness here. There's a test for this, and it's called Little's MCAR test. This is Rod Little from University of Michigan. Developed a test. The MCAR acronym stands for missing completely at random, which is different than just missing at random. There's some levels of randomness here that are defined in the books. The only one we really need to care about is this one, and it's a chi-square test to determine if the missing data is indeed completely random. And that completely random just means not dependent on your who you are or what variable it is in the data set. So for example, if only women in our data set have missing data for some reason, then the missingness is going to depend on the fact that they're a woman. Or if there was a particularly sensitive question in the data set, maybe people left that one blank, and so there's a lot of missing data on that one, then it would be not random because it would be dependent on the fact that it was on that variable. So completely random means not dependent on variables, not dependent on participants, not dependent on anything. It's just missing because, well, there was just some random missing data in there. So there's a test, and it gives you a p-value. 0.05 or less indicates that the data is not missing completely at random, and you should probably figure out why. So this is a rejection of the null hypothesis that the data is missing at random, thus concluding with the alternative, if the p-value is less than 0.05, that is concluding that the data is not missing completely at random. So I have a sample data set here I'm going to show you. This is your data set here. It's a practice data set that I have posted on our Canvas page. And basically, this is like 3 columns. The first column is a case number. just participant number. Second column is on a scale of 1 to 7, how fashionable do you think you are? And then the third column here is on a scale of 1 to 7, how important is basketball to you? And so this is actual, this particular variable is an actual variable I've used in my research, maybe not the fashion one, but theoretically we have a zero correlation between fashion and basketball importance, but you never know. So we can do a scan for missing data first, and we already see a couple here, right, in the beginning. And I'm just literally going to go scroll down, and you can tell in this data set that participants 82 through 98 did not fill out the basketball item. And so you can see we have some missing data, and we can probably already tell that it is not random, right? Because all the missing data points are on variable basketball. So we can run this test, but we already kind of know what to do, and that is to identify these missing values as basketball items. So we're going to get into we're going to treat this like real life. I'm going to scroll through a few more slides here talking about strategies for missing data, and then we're going to decide what to do. So what if 5% of your data or more is missing, and what if it's also not missing randomly? So there's two scenarios here. One is, there's actually three. Scenario 1, less than 5% of your data is missing, no problem. Scenario 2, 5% or more of your data is missing, and it's random, so that's okay. That's kind of okay as well. And then number 3 is 5% or more is missing, and it's not random, and so that's sort of the one where you have to take the most care to either get rid of those people or enact one of these strategies. But either way, these strategies are going to be important regardless of the scenario and the percentage of data missing. The first one is list-wise deletion. This is just getting rid of people if they have any missing data. And so this is good if you have lots of data. In our sample data set, we do have 98 participants, so we could probably get rid of a few, but our data set is also quite small in the number of variables that exist. So maybe we need to keep those people, or try to. You guys couldn't see that, I was taking a drink. Okay. Prior knowledge is used when a researcher, this is funny, replaces a missing value with a value from a well-educated guess. So this is sounds very unscientific and even unethical. But a well-educated guess is one where maybe there was reason to believe that the people who were missing a certain value just couldn't complete the data set that day because, and you were there present in the experiment, something happened that you saw, and so then you knew what they were going to say, but they couldn't. They shouted the answer as they were leaving, as opposed to writing it down on paper. Something where you know what the data's, have a legitimate knowledge of what that value should be. But if you don't have anything that's well educated, if it's just a guess or something not scientific or not official, then you should definitely not do number 2. So we're going to move on. Number 3 is mean substitution. So this is like, okay, I want to keep this person in the data set. What do I do? What's the best guess at the value of a person or that person's response on a variable? Well, you just take the mean of that variable. The mean, in the absence of all other info, is the best guess. Number 4 is a little bit better, and I'm not going to go into the particulars of what this algorithm is, but you guys are free to pursue more information about this on your own. This is a fancy procedure, as it says there, that fills in missing values based on what might be expected. So what might be expected is based on, okay, you have the mean for that variable, but now also you have the mean for that person. And then maybe you have the standard deviation of that variable and the standard deviation of the person. You can factor in patterns of missing data that way. The other way to factor in a pattern is to look and see, oh, okay, if this is not random, then maybe, like we said earlier, maybe all of the variables are missing, or all of the missing data occurs for one variable. So maybe we can see a pattern there and see, okay, well, every single person was answering 7 to this particular item after 3 p.m. on Friday. And so if everybody was answering 7, that's sort of like, well, that's a well-educated guess, number 2, that maybe that person would have also answered 7 since it was after 3 p.m. on Friday. Or you can run the expectation maximization EM algorithm, and that algorithm will then fill in a 7 for you because it sees the pattern itself. And so it's sort of like a machine learning kind of way to fill in missing data rather than relying on person knowledge, which would have been number 2. And it's also a more fancy version of number 3, which was the mean substitution. Okay, so before we get to the next round of things to screen for, let's go ahead and do this missing data stuff for our particular data set here. So you can count. One way to figure out what the percentage of missing data is just to count. You've got 2 here, and then you've got, let's see, 82 through 98, that's 17 more, so 19 missing out of 98, that's greater than 5% on that basketball variable. So in that sense, if we're screening for missing data in a univariate sense, then we have far more than 5% because we have 19 out of 98. I just did that by looking at the data set. I'm a big fan of just looking at the data set and trying not to jump to analyses now that I've been trained by many others who have told me the same thing. Sorry, again, I was taking a drink. But we can also run some frequencies to count. So this is useful if you have a larger number of data points missing, or if you have they're like scattered around the data set, and so you can't necessarily go and find them so easily. So you can just run some frequencies here. I'm going to put fashion and basketball over to the right and just display frequency tables like so. And so we're going to see, it should give you a percentage. Well, I guess it just gives you a total. The percentage is down here, 19.4%. In the top box that I was expecting there to see the percentage, it's just a total. So 19 out of 98 are missing on basketball, and for fashion, 0 out of 98. So you would take 19 and divide that by 98 to get your 19.4%. Okay, so that's your first check. We're like, more than 5% are missing, so what do we do? Okay, so the thing we need to do here is the MCAR test, the missing completely at random test. And so to get that result, we're going to go to Analyze, Missing Value Analysis down here. And we're just going to move fashion and basketball over to quantitative variables, selecting the EM box there. That's not necessarily to run the EM algorithm, that's just to get the MCAR test, which will print kind of strangely multiple times here as it goes down the output. So let's see what happens. We're going to get your summary of estimated means and standard deviations and things that are not as useful as just the test result. So let's go to, it's going to print it 3 times here. You see under EM means and covariances and correlations. You see Little's MCAR test here in small print equals 0.364. That's your chi-square test statistic for the MCAR test. And the interpretation comes from the p-value, as are in the notes here. If p is less than 0.05, our data is not missing completely at random. And p here is at the end here, sig 0.546. So indeed, the data is missing completely at random. And in this case, it's just, we just put those 2 variables over there. So what that is telling us here is that essentially the missingness on the basketball variable is unrelated to one's response to the fashion variable. Even though we have more than 5% of our data missing, we can say that the data is missing completely at random, and we can move forward here. Now, the strategies that follow for missing data, then what this calls for is like, well, we could actually, since it's missing completely at random, the data is missing completely at random, we could actually just leave it in there if we want. We could just leave the data as it is. There's not going to be an impact on our analysis that is any more dramatic than there would be if less than 5% of our data is missing. We've also determined that there's nothing in the fashion variable that is related to the missingness. So if we're going to then relate our fashion variable in some way to our basketball variable, that's going to be okay. And in fact, if we just ran a correlation between them, let's say, it would just SPSS would automatically listwise delete those people with missing values. So in the end, list-wise deletion is going to be employed if we're going to run an analysis of that sort. And I think anything else is sort of unnecessary. For example, prior knowledge, we don't really have prior knowledge in this case. Mean substitution seems like a stretch because we're plugging in the mean for like 19 people on a variable that has some variance to it. So that doesn't make sense to me. And then the EM algorithm, that could work, that could be interesting here, but we do have a lot of data. So we're going to go ahead and just let it be for now, and then let SPSS listwise delete automatically if it needs to. Okay, so next up is things to screen for univariate outliers and normality. So we'll get into that. So we're going to start by printing descriptive statistics. This you guys have probably done many times in your statistics career by now. Print descriptive statistics in various ways. And so what we need to do here is do this so that we can try to figure out if one of our data, one of our variables is skewed and otherwise strange, if there's some outliers in there and such. So here's a list of descriptive stats that we'll need. We're going to kind of overdo it here at the beginning of class, making sure that you guys run through descriptive statistics for all of your variables as practice. Later on, when we get into analyses of more than just a couple of variables, I'm still going to need you to print all these, although it may not. You may not need a histogram for every single variable later on in the class, but you can always ask me later on. So anyway, we're going to do this for our two variables here in the example. So we're going to do go back to frequencies. We actually already did a frequency printout here, so I'm just going to add in some of the statistics we need. So you click on statistics, you click on mean, standard deviation. What else do we need? Skewness, kurtosis. There's also median and mode and things like that. I'm going to leave it at these four for now, and click continue, and then click on charts, and go for a histogram here with a normal curve on it to finish off the description here. So continue and OK. And we're going to see SPSS is taking its time. Okay, so here's your frequency distribution again, and this time you've got some statistics in there with means and standard deviations, and also skewness and kurtosis values. And then if you scroll down, you'll see your histogram here for fashion, and then another one for basketball there. So you can start to judge from the histograms. They look somewhat normal, the basketball one, and actually both look positively skewed, but there's also a strange value out here for fashion that will need to be addressed, it looks like, way out in the positive end. So let's go back to the notes and get some wisdom from there. Red flags are extremely high or low skewness and kurtosis values. What is extremely high or extremely low? Well, that was skewness illustrated. This is kurtosis illustrated. Kurtosis it's always hard to describe. It's like a high kurtosis is one that's kind of fat on each end and then suddenly goes up in the middle, thus indicating a lack of normality. The low kurtosis is like fat in the middle with a very gradual tail on the end, something like that. Anyway, we don't need to analyze the graphics too much. What we do need to do is calculate z-scores for skewness and kurtosis each time. So these values are all reported in SPSS. You take your skewness value, which I'll show you here in a minute for our example, divide by the standard error of skewness. Same thing for kurtosis. You take your kurtosis value, divide by its standard error. And so if you get something that's greater than 3 or less than -3, that's a red flag. That means that you need to look into that variable. It may not mean that you have to get rid of that variable or do something to it. It just is a red flag. It means that we need to pay attention to it. So in large samples, larger skewness and larger kurtosis values might still be okay. And this is where a graph might clarify for you. So if we have skewness, then we go and we look at what might have happened. So we might have impossible values that probably should have been screened already, but sometimes they sneak in there, and then legitimate outliers. So step one is to is to look at the skewness and kurtosis values. If you get the positive 3 or greater, or the negative 3 or less, then you follow up with a second z-score, and this is just to identify outliers, and they're similar to each other, these rules of thumb. But once you've identified that you have a skewed variable, then you go in, you look at your outliers, or the highest and lowest values in your data set. If you have a positively skewed variable, you look at your highest value. If you have a negatively skewed variable, you look at your lowest value. And then you calculate the z-score for that particular value. So you take that value, subtract the mean on that variable, and divide by the standard deviation. And if that z-score is extreme, less than 0.001 on the normal curve, or less than, 1,000th of the normal curve, or just more simply a z-score of positive 3.29 or less than negative 3.29, then that's a potential outlier, and we need to identify it as such and, again, make some decisions. So again, with large samples, these can be relaxed a bit, these rules. Okay, so if we have an outlier, what do we do? Suppose it clears that 3.29 criteria. Well, number one is just see what happened. Maybe there was an error in the data entry. That's where prior knowledge comes in. And that's often, in my experience, been the biggest strategy to identify an outlier and what to do with it. Number two is to listwise delete if you're like, well, I don't know what happened and it's weird and this value doesn't make sense. We just need to get rid of this person. So we do that. And some of this is, again, a little bit unscientific, but you just try to be as scientific as you can to avoid any sort of skepticism from the readers of your poster or the reviewers of your research paper. Number three here is to decide if the cases that are outliers are properly part of the population. So this is assuming that you keep the outliers, and you're like, well, okay, I'm keeping this outlier, but it's part of the group of, in this case, basketball players that I wanted to sample. Maybe this person really just is really into basketball, and I want to measure those people, and they're scoring high on that particular variable. It really, really matters to them to play basketball. Well, then let's measure them. If they're not, if this person stands out in some way, or is just like you measured like a 12-year-old kid in a sample of adults or something like this that doesn't make sense, then you can delete them with a clear conscience. Number four here is to keep the outlier but change its value. This one is tricky. It's like you're making something up, changing its value. But I've seen this done where let's say you have like a drug use variable, and you have like 0 to 1 times used per month, 2 to 4 times per month, and then 5 or more, and then you get someone that's like, I don't know, like twice a day, so like 60 or something like that. Hopefully you don't have those people if you're studying drug use. Maybe you want to study that person. I don't know. Either way, that 60 should probably be changed because it's such an outlier, and what it could be is put in the 5 or more category. And so it changes the impact because the 60 is the same as a 6. But in this case, it makes sense. They're just sort of in that highest category. And you don't want to distinguish, let's say, that 6 from that 60. Then you can change it. But otherwise, it's tricky, and you probably want to get the advice of your collaborator, supervisor, if you're changing outlier values around. Number 5 is to keep the outlier and then transform it. This is the fancy version. For example, taking the square root of a positively skewed distribution makes it look more normal. There's different, if you go to the books, Tabachnik and Fidel, for example, have these different recommended transformations of variables. So you can take square roots, you can square things, you can do various algebraic transformations that make your distribution look more normal. Well, I just have that the interpretation here gets sometimes pretty goofy or strange. So like, I think that the correlation between fashion sense and the square root of basketball interest is going to be significant. It's hard to interpret sometimes. So I'm a psychologist. I try to stay away from things that are hard to interpret in terms of hypothesis tests. So in that sense, I usually recommend number 5 with caution. But in certain fields of psychology, I think this is more common than other fields. And in my field of sports psychology, I rarely see this. So if you've seen this, or if your advisor recommends a transformation, then I'm kind of excited because it's it's going to be interesting to interpret and fun and different. So you can come to me and we can have some fun with it. But again, I recommend this strategy with caution. Okay, so before we move on to multivariate outliers, let's back up and do the univariate check for our data set. So we've got our descriptive statistics printed. So what is next? What is next is doing this skewness check and kurtosis check. So we have these values here for our data set. And I'm going to privately get my calculator out here. You guys can do this at home if you're following along or wherever you are in the classroom. Okay, so your skewness value there for fashion is 8.452. That's pretty high. And so what you're doing for this example, you're going 8.452, and yes, I'm doing this on my calculator, divided by 0.244. And I didn't actually need a calculator to be able to tell that that's going to be greater than 3. So we have a skewed fashion variable. And then kurtosis, 79, that's a big value, 79.415 divided by 0.483 is going to give you 164.4. So it's wildly kurtotic here as well. So something is up with that fashion variable. For basketball, you do 0.763 divided by 0.271. You're going to get 2.82, so that's just barely not skewed. And with such a large data set, you're pretty much okay on that one. 0.535 divided by 0.535 is for kurtosis, and you're going to get 1 there, or -1, I should say. And so you're good on the basketball variable. But on the fashion variable, you have skewness and you have kurtosis. Okay, so I'm going to move forward here. Why might a data set be skewed? Impossible values or outliers. So let's look. If you just look at the frequency table there, you're going to, or if you just went back to your data and scan that, you're going to notice that there's a 44. Okay, so in this case, it's easy to diagnose. We have a 44 that was probably just a mistake in the data entry or something along these lines. And if you guys use Qualtrics or something else, psych surveys, this will be impossible, and that's the beauty of online surveys these days. But sometimes if these things get entered in by hand by a research assistant or something like that from paper, translated from paper, then you might see this where, for example, you're going across and you go 4 and then you go 4 here, and this should have been a 4, but it wasn't, and so then you typed it twice. Okay, so we don't really know what happened. I'm not giving you any information here, but we suspect that this is like should have been a 4, but it's either way an impossible value. So we've determined that. So what do? Well, we can run the outlier check just for fun here. The 44 gets entered into an analysis where we check the z-score. So we already know this is an impossible value, so you don't necessarily need to do it if you know the scale is on from 1 to 7. But here we go. We're going to do 44 minus the mean for that variable, which is 5.3. Here we go. I'm doing this on my calculator again. We get 38.7 on the top part of the fraction. Then you divide 38.7 by the standard deviation, which is 4.15, and you're going to get 9.3. So this 44 is clearing the z-score criteria. Technically, you need to do that before you make a decision, because if we've identified a potential outlier and it doesn't clear that 3.29 criteria, then, well, maybe we can just leave it in there, even if the data set is skewed afterward. But here we've got an impossible value, and it's also a clear outlier. Well, I'm going to, in this case, go with number 1. We're going to say that there was an error in the data entry, and we're going to, because it's a 44, I think you can safely say that this should have been a 4, regardless of really knowing what happened. And so I'm going to change it to a 4, I think. In real life, though, you would need to, again, check with your collaborator, your supervisor, see how the data was collected, and confirm that. And if you cannot confirm that, in a large data set such as this one, list-wise deletion is probably okay, I would say. You can afford to lose one person, certainly, especially on that fashion variable where you have all 97 other people who have filled out their numbers. So I think you can do either one for this one. In real life, you could do either one. And so if you're making a decision for your homework, you just need to put in a sentence or two to justify what you've done. And maybe run it by me before you turn in your homework. So I'm not going to bother with number 3, number 4, trying to replace the value with something based on an algorithm or based on a maximum or minimum. I'm just going to change that value to a 4. And so I'm going to go in and do that right now. Here comes the 4. Okay, so we made our decision, and then we can proceed. So the only thing left to check is for multivariate outliers. And for multivariate outliers, we run the Mahalanobis distance calculation in SPSS. So I'll show you how to do that. This is based on, so people wonder, first of all, how to pronounce it, Mahalanobis. Second of all, why it's called that, and it was, this is a statistic named after Prasanta Chandra Mahalanobis, who was the founder of a statistical institute in India, and there he is. You can look him up. This has sort of become the standard way of calculating or determining whether there are multivariate outliers in a data set. So this is theoretically, and I guess conceptually, we have a centroid. So if you imagine 3-dimensional, it's like a solar system or something, and if you like have the centroid is like a 3-dimensional thing in the middle of the solar system 3D space, and then you have all of your multivariate cases in your data set floating around this center, and the distance, like in one direction, is based on one variable. Distance in another direction is based on another variable. This is a concept that goes along with the idea that it's just sort of like multivariate space, and so someone could be really close to the center on one variable but really far from the center on another variable. And so if you have an infinite number of variables, you have an infinite amount of directions that could be drawn from the centroid here toward those various, in the direction of those various variables. And so if someone's really far away from the centroid, then they have a large Mahalanobis distance. If they're really close to the centroid, then they have a really short or small Mahalanobis distance. Conceptually, that's what Mahalanobis himself came up with for this. Taken together, this forms a chi-square distribution. So chi-square comes back again. We saw it with the MCAR test. Now we're seeing it with the Mahalanobis test. The degrees of freedom here are equal to the number of variables in your data set minus the case number. So it's basically all the variables that you're interested in evaluating for outliers. You have, in this case, 2 for our example. I forgot to make this bigger again. I'm going to make this bigger for a while. Okay. If a case's Mahalanobis distance is extreme, then it's a multivariate outlier. And if it's far away, in this case, you have a chi-square distribution, like I mentioned, and if the p-value is less than 0.001 on that distribution for that value or for that person, then you've declared it an outlier. So once you've identified your outliers, then you can go back to the strategies here. So we'll do this again for the sample data set in a minute. So first of all, you see what happened. Maybe there was an error again. But this is less likely because, like, for a multivariate outlier, we already corrected that 44, right? So like that person might have shown up as a multivariate outlier before, but now that we've corrected the 44, well, they're probably not going to show up anymore. And so then once we've done the univariate check, in this case, maybe we might not have a multivariate outlier. And so we've already done number 1. Number 1 usually occurs in the univariate stage, in other words. But it's always good to go back and look, and so if somebody shows up later as a multivariate outlier, you can go back again and look, try to figure out why. It's always good to just look. Number 2 is listwise deletion. This is more popular because, well, it's just harder to identify why or what happened with that person that caused them to be an outlier. But suppose you go back, you look, you identify a certain pattern, then maybe you go to number 3 and you're like, well, this person was really high on all of my variables collectively, really unique, but they're also still part of the population I intended to sample. If they still stick out, however, then maybe you go back and listwise delete them. Number 4 is to keep the outlier again and change its value, but again, this gets harder. So number 2, I think number 1 is less popular for multivariate outlier screening. Number 4 is also less popular because, well, you have to change multiple things, and so then it gets really dicey. This is the point where I send you back to the data set here, and we practice these things and we make a decision. So we're going to go to the Mahalanobis distance. To do this, you're going to go to Analyze Regression Linear. Now, you're not actually doing a regression here. You are doing a regression, but you're not doing it because you want to do a regression. You're doing it so that you can get the Mahalanobis distances printed in your data set so that you can then evaluate. So you're going to go to Analyze Regression Linear, and I'll show you what I mean. You're going to go case number on dependent, and then fashion and basketball on independent. That makes no sense in a regression context, but what you're doing is you are selecting the variable in your data set that means nothing, case number, right? It's not a variable for analysis. You're just selecting that, putting it in the dependent variable, and then all of the variables that you're actually interested in as far as evaluating outliers, they go in the independent slot. And so in this case, that's just your fashion and basketball items. And so then that's going to allow you to evaluate multivariate normality for those two items, or for those two variables. The key here then is to go to Save and go to Distances, and there's Mahalanobis sitting there among other things here that you don't need for now. You're going to click Continue and click OK. Now there's one tip that I will give you. If you're in a data set and you don't have the case number variable, you can create it. And then I've seen my past students creating this case number variable, and they go 1, enter, 2, enter, 3, and it's really annoying. So there's a better way to do that. What you do is you go to, you also cannot do like the same number the whole way down, like 1, 1, 1, 1, 1 the whole time, because then there's no variance to that variable, so when you run the regression, it won't work. So what do? You go to Microsoft Excel, and this is one way to do it anyway, and you go and like type 1 in the first cell, and then below that you go equals, click on the 1 and go +1, and it gives you 2, and then you copy paste that down all the way, and then it'll give you like a case number variable all the way for as long as you need, however many cases you have, and then you can copy paste that from Excel over to SPSS. So if you didn't follow that as I was just talking into the video here, just come and talk to me. Another thing you can do is just go 1s all the way down, and then like change one of the variables to a 2. As long as there's a little bit of variance in there, it will work as the dependent variable in this case. All right, enough talking. So I'm going to click OK, and you're going to get output. That doesn't matter. You're actually just going to go right back to your data set and look at Mahalanobis distances here that are printed directly into your data set. So these are values of multivariate normality that are then plugged into your data set, and so each person gets their own. And so we just need to go to the criteria then, and so you're going to go to the chi-square table. Okay, so I just Googled chi-square table and pulled it up here. This is your criteria for evaluating your multivariate outliers. And so we said in the notes here we have 2 degrees of freedom because there's 2 variables of interest. And then the criteria is kind of conservative, meaning we need really to have an outlier in order for it to qualify. So the 0.001 here gives you a 13.816 for the criteria here. That is 2 degrees of freedom, and 0.001, that's your critical value for chi-square. So if we go back to our data, we're going to look for something greater than that value. And how do we do that? Well, we can scroll up and down this variable, or we can just sort the cases by this particular variable to get the highest one at the top. So we go sort cases, put Mahalanobis over. My computer is reacting very slowly. Mahalanobis over. It knows it's on camera. It's getting nervous. Descending order. Click OK. And go back to the data again, and you see the highest one is 8.63. Okay, so that's not above the criteria. It happens to be case number 12. That person answered 1 to each of the responses. So you can see that they stick out, right? They were the only person that did that, and so then the test is doing its job. It's identified this strange person, strange because that was the only person that did that. However, it's not extreme enough to qualify, and so we don't have to do anything. If, however, you did have something there, then you would have to enact one of these strategies that we talked about here. And also, if, for example, we had left our 44 in there, then maybe we would have needed to do something there as well. Okay, so from here, typically you need to make sure you rerun your descriptive statistics to see what happened, like it's before and after. So I'll leave you guys to do that. You know how to run descriptive statistics, so you got to make sure that your skewness and kurtosis have come down, which in this case I'm sure they would have. And then the only other thing to talk about here in the notes is the homogeneity, or I don't know why they call it homogeneity. It's like a fancy word meaning equality. But anyway, the equality of variances check. And this is important when you have two or more groups that you're comparing, as in like an ANOVA or a t-test. So the variances must be roughly equal across groups. So if you're comparing two groups, this is one of your assumptions of a t-test or an ANOVA. If you're comparing two groups with a t-test, let's say, or three with an ANOVA, you need to make sure those groups have roughly equal variances, because if you're going to compare their means, that comparison needs to be meaningful, so to speak. Like if you have two means that are similar, but one of the variances is extremely high, then that really doesn't tell you much, because the variances are so unequal. So it kind of kills the drill as far as comparing means of groups, which is ultimately your goal. So how do we do this? Well, we just go back and look at our variances to make sure that they are roughly equal to each other. So that can come in descriptive statistics. When comparing continuous variables, variances must be roughly equal across, which is the assumption of homoscedasticity, another fancy word. Here for a t-test or an ANOVA, we just take the largest group variance divided by the smallest group variance. This is called the F-max test. And an F-max as high as 10 is good. You want them to be relatively equal, but if for the textbooks here, the less than 10 rule tends to be the one that people quote in research papers if they need to justify comparing two groups that are a little bit different in their variances to each other. So from here, what you would do is you would take your fashion and basketball variables, if those are the two that are to be compared. You just do descriptive statistics, get the largest group variance, and divide it by the smallest group variance, so the larger one divided by the smaller one. And if it's less than 10, you would move forward with a t-test or an ANOVA, depending on what your goal is. So suppose here, since it's the same people over time, we have a repeated measures ANOVA or a dependent samples t-test. On these two variables, you would run this F-max test, you would get a value larger than 10, and then you would proceed with your comparison of the two groups. And you would also want to note if this was different. So like for us, it would be before and after the 44 deletion. Would it have mattered to have that 44 in? My guess is that it would have, so you would run the variances with and without the 44. You'd probably get an F-max failure for the 44 with the 44 in there, and an F-max approval without it in there, and so on. And then you would want to write that into your process of data cleaning or screening, followed by analysis. Okay, that's all I got for now. I'll see you in the next lesson and in class.